Next one is Benjamin. He will talk about first empirical measurement of the iron 11 and 14 freezing distance.
Actually changed my title a little bit since we submitted. Right? Made it a little simpler for you guys. So yeah, I'm Benbow. I'm gonna be talking about my work of the first empirical measurement of the coronal freezing distance, and I did this work advised by S.Habbal. All right. So this, as of course you all know, is the sun. And the sun has two main components that we can observe in optical wavelengths. The first being obviously the photosphere, which is quite cool and dense. And then we also have the outer outflowing atmosphere of the sun, which we call the corona. And in the corona, there's some interesting behaviors, especially with the incredible density drop-off that you get from the photosphere as you flow outward into the outer corona. Several orders of magnitude, very rapid drop in density. And this rapid drop also then causes a huge pressure gradient that accelerates particles to several hundred kilometers per second and pushes them out into the solar wind. And then, of course, the corona is much hotter than the photosphere, the temperature spiking quite rapidly to 1 to 2 million Kelvin, but then it remains roughly constant throughout the corona as the solar wind flows outward. And this is a cute little one-dimensional model that explains the solar wind quite well, but of course, life is never simple because magnetic fields. So the sun, of course, has very complex magnetic fields, different types of morphologies that you get. Some of the main underlying structures that are kind of always on the sun have to do mostly with lower order magnetic moments, such as the magnetic dipoles. You notice in the polar regions, you tend to have these kind of diverging field lines that go directly from the photosphere outward, compared to the more equatorial regions where you tend to get a little bit more bound, loopy field lines. And if you even look at some higher order moments, you get even more of these kind of loopy regions. But the important thing is that you kind of have these fundamentally different magnetic field morphologies that the solar wind is experiencing while in the corona. And this ends up actually resulting in two fundamentally different types of solar wind that we observe very far away. So the first type happens in these regions where you have radial field lines, and we call these coronal holes. So far away from the sun, we observe a solar wind density that's very low, a temperature that's about 1 million Kelvin, and a high outflow velocity. And again, remember, this is flowing basically unperturbed from the solar surface all the way out into the solar wind. Now, the other type of solar wind that we observe far away from the sun comes from these solar streamers. So this solar wind tends to have a higher density, higher temperature, and a lower outflow velocity, about half that of the coronal holes. And the fundamental difference in how the solar wind is forming in these regions has to do with the origin. So again, in the coronal holes, it's coming straight out, whereas in the streamers, you get these bound loop structures where plasma is trapped in these structures. But then at the very top, you get some magnetic field lines that reconnect, and from the top of these structures, the wind then flows outward. And so if you imagine that you're a particle in the solar wind and you're experiencing this incredible density gradient, at first, when you're near the photosphere, you're going to have lots of collisions, which are going to be ionizing you, knocking electrons off. Electrons will come along and recombine with you. Your state is constantly changing. So you're not at any one ionization state, but you're constantly being thrown all over the place. But then very far away from the sun, as the solar wind is flowing outward, there's no more particles that are nearby to you, so you stop having these collisions, and whatever state that you're in remains constant as you flow outward. And the transition between this collisionally dominated and collisionless regime we call the freezing distance, which is due to the fact that we're saying the ions are freezing in their state. And so this distance is very important for solar wind models, and they've tried to make predictions of what it might be, but no one has ever actually observed it before. And so the logical question would be, well, why haven't you observed it? And it's really quite a simple answer, is that we just can't under normal conditions. So here I have a little video of the best data we have right now of the sun. So SDO looking at the solar surface, or a coronagraph blocking the sun. This is SOHO. They're actually synced up, so you can see there's an eruption here that then propagates out. And this is actually on the day of the eclipse that I'll be talking about later. And so there's this region in between the two data sets where we just, due to the high contrast of the sun, cannot observe yet with our current technology. And because life is hard, the freezing distance, of course, is supposed to be located inside this unobservable region. So in order to understand how the solar wind is evolving and how these, how we can link what's happening on the solar surface to the solar wind, you have to kind of be able to tie these two data sets together. And we can do that conveniently with solar eclipse data. So when a total solar eclipse happens, the moon blocks the sun, and we can then measure the corona all the way down to the solar photosphere. And this line here is showing the predicted freeze-in distance that I showed earlier. So the data I have is from 1 year of solar eclipse, from the 2015 eclipse in Svalbard, Norway. And we have images centered on optical emission lines from both the iron 10 plus ion, which I'll call iron 11, as well as the iron 13 plus ion, which I'll call iron 14. And the convenient choice of these two ions was due to their peak ionization temperatures of around 1 and 2 million Kelvin, which means at those temperatures, they will be the most abundant species of iron. And again, the choice for these is because these temperatures kind of span the typical temperatures you expect to see in the corona. So they act a bit like a little thermometer. So in order to then measure the freeze-in distance, what I'm going to do is take a ratio between two different images. Specifically, each ion has an on-band image where it's a 5 angstrom narrow-band image of the corona centered on an optical emission line, and an off-band image that's an identical setup, but the wavelength has been shifted by 10 angstroms, so you're outside of that emission line and can therefore measure the continuum background. And so to get a sense of what the intensities of these images represent, the on-band essentially represents the ion density involved with the electron density, whereas the off-band looks at the electron density alone. So if you take the ratio of these two, you get essentially a dimensionless density of the ion relative to the background electrons. And the reason we want to do this is because, of course, the density is dropping exponentially with the outflow, but you want to measure any enhancements or depletions from that drop-off in order to tell if any more of this ion is being created or destroyed. So the point at which this ratio is flat, or not changing anymore, is where you say the plasma has frozen in. So what I've done is to develop a graphical user interface to identify individual lines, field lines, of outflowing plasma in the corona. And then along these lines, I measure what that ratio is. And then there's an algorithm I wrote that then determines the point at which this line is sufficiently flat and measures that as the freeze-in. And so I can do this for various different regions in the sun. You'll notice sometimes in a more magnetically active region, there's sometimes density enhancements of the ion. There's more behavior going on there. But in the end, they always freeze out and go relatively flat. So I then repeat this procedure many hundreds of times around the entire corona for both of these ions. This is the hotter iron 14 and this is the cooler iron 11. And down here we have a two-dimensional map of the corona. So this is just turning polar coordinates to Cartesian so you can see the differences in freeze-in a little better. So what you'll notice first off is that near the, I should say, I then bin this data into 4 quadrants just to give you an idea of how the polar regions are acting differently to the equator. The actual boundary between these is not well defined, but it's just kind of give you a little idea of what's going on here. So in general, the equatorial streamers tend to have a much higher freeze-in distance than the poles. And in fact, the hot ion, the iron 14, has a nice almost sinusoidal behavior to its freeze-in as a function of latitude. Now the peculiar thing though is in the cooler ion, the iron 11, the eastern streamer area is slightly large, has a slightly larger freeze-in distance than the polar poles, but it's not super significant. Whereas the western region, in fact, does have a slight enhancement. And I should also note we, unfortunately, due to a misalignment of the camera during the eclipse, lost this portion of the data, which is why we cannot measure the freeze-in in that portion. So we've now measured the freeze-in, and we've noticed some interesting properties about it. And really the most startling one is, why is this east wing behaving so strangely? Or at least we can't explain it right off the bat. And so in order to understand this a little better, you interpolate the data that I just showed and then plot it on top of the white light image. And I should review a little bit. So in the polar holes, you'll notice that the hotter ion freezes in quite close, as I said. The colder one a little bit further out. So what this probably means is that the temperature is around 1 million Kelvin. It's not creating a sufficient amount of the hotter ion for it to be frozen out further, compared to the colder ion, which is created in a little bit higher abundance, but still freezes out quite quickly because the temperature and densities are lower. Whereas in the equator, you have a much hotter temperature, which is creating more of this iron 14 and allowing it to exist and change further out into the corona. But again, this eastern region is quite peculiar, and if you zoom in a little bit, you'll notice that there's also presence of these large prominences all along the eastern wing. And for scale, I put Jupiter here, and then the Earth actually fits inside of that prominence. That's to scale. But so the interesting thing about prominences that Shadia and collaborators have noted before is that it causes magnetic turbulence in the corona above. So what we think might be happening is that the magnetic turbulence may be mixing the plasma and heating it to a higher temperature. So to get a better idea of what I mean by that, if you look just at the hotter iron-14 image and just isolate the two equator regions, you'll notice in the west that there's these dark wedges, basically small coronal holes that are embedded in the streamer region that are at a lower temperature. So remember, this ion exists mostly around 2 million Kelvin. So if there's no emission here, it means that that plasma must be significantly cooler. Whereas if you look in the east, there's really not a presence of any of these large holes. Maybe there's one here, but it's a lot smaller and it's sufficiently more mixed. And so because of this, what's probably happening is that all of this plasma is getting lifted up to 2 million Kelvin compared to this, where you have patches at different temperatures. So in the west, what's happening is both ions are being created in different regions and surviving further out, compared to the east region, where the iron-11 is being entirely ionized or largely ionized. And so to push this point a little bit further, if you look just at the density profile itself, so this is the same ratio I've been talking about, except now instead of drawing it down a field line, I've drawn it in a circle around the corona at 1.5 solar radii. And you can see it on the map here, that's what the line is. And what you'll notice in the iron-14 is that you get this kind of, again, almost sinusoidal density profile where you have higher densities in the equator compared to the polar poles. And remember, this is not bulk density, but ion density relative to the bulk density. Further, in the west region, the iron-11 is highly enhanced compared to the whole regions, but the eastern region does not have a significantly higher density. It is a bit higher, but it's not nearly as high as it is in the west. And so again, this supports this idea that in the east, the iron-11 is being ionized to more highly ionized states. And further, if you examine closely, you can actually see that where these holes were in the hot ion image, they're actually fully covered up in this image, because this is representing the 1 million degree plasma. And so you can see that actually where these holes are located in this, you see there's a density drop. And similarly, in the exact same location, you get these huge density spikes in the iron-11. So there's this trade-off of which one is more abundant based on the temperature, which of course makes perfect sense based on the Saha equation. But it's cool to actually be able to observe that and explain why different regions must be at different temperatures. So in conclusion, first and foremost, this is a novel measurement of the freezing distance and a novel method for doing so. It's never been done before. Secondly, we found the freezing distance is highly variable, unlike what models predict. Of course, when they do one-dimensional models, they don't consider how different structures may affect the freezing distance, namely that it's not at all spherically symmetric. In general, the streamers tend to have a slightly higher freezing distance than the coronal holes, but this is not a hard and fast rule, because sometimes dependence on temperature may dominate, as we saw with the iron-11. Further, prominences appear to be having an effect of heating and or mixing the corona above, and while this is still kind of a qualitative speculation at this point, if to answer this question fully, we'd want to do some in-depth hydrodynamic modeling and really try to really quantify what this means. And then further, that the ion density in the streamers tends to be enhanced compared to the polar holes. And finally, that all of this information is completely consistent with what's been observed far away from the sun with spacecraft. So for the first time, we've been able to really link through what's happening on this disk of the sun and how these different structures are affecting the formation of the solar wind, and then explaining why that leads to different solar wind particle behavior far away from the sun. So hopefully in the future, maybe this could be used possibly to try to make predictions of the solar wind and other things like that. But that, again, that would be speculation. And since I'm noticing I have a little bit of time, I will talk briefly about some future work that we're going to try to do. So one thing to note is that I keep talking about this dimensionless density, and if we could get a calibration, we could potentially, so these numbers basically are not comparable to each other. It's only comparable within the same image because we have not absolutely calibrated the data. However, we're going to attempt to calibrate them at least to each other. in that sense, we could then say, what is the absolute relative abundance of these two ions? And using that information, we can go back to the peak ionization curves and actually make a temperature and density map of the entire corona. But that will take some more work, and we'll have to figure out how to properly calibrate the data for that. But yeah, so at this point, I will take some questions.
Thank you. Okay, here.
Is this the only eclipse for which you have data on these lines?
That's a good question. No, in fact, there are more. We wanted to focus on this one and get as much out of it as we could before moving on, but that is definitely something that we can do. I think there's at least 3 or 4 more years, and what we could do then is span the solar cycle and potentially start to quantify maybe how the solar cycle is also affecting this freezing distance and densities and other things like that. But we wanted to have the first step really be to get everything done on this 1 year so that moving forward we know what we're doing when we look at these other years.
Jeff, would you like to ask them?
So when you think about mechanisms, and you mentioned turbulence, have you thought about how you would separate the effects of, unfortunately, the prominences occur often above an active region where you might imagine that the magnetic field is stronger. Have you thought about how you would separate this sort of turbulence MHD effect with the prominence from just the general fact that the magnetic field is stronger there?
Yeah, so that's a good question. I think the point I was trying to make with the prominences was not that it's not necessarily the strength or the activity of the magnetic field that is the crucial point here. So this, for example, if you look in the western region here, you still have quite a large magnetic activity. It's more that the magnetic activity is well defined. So you have these well-defined streamers, well-defined loops, where inside the magnetic activity is quite intense. Whereas with the prominences, it kind of breaks down this field structure, and so you don't get these clean field lines. So I think it's more to do with that it's just ruining the clean morphology and causing the hot plasma to be pushed into the cold plasma, whereas in the other quadrant, the field lines, the strength of the field is actually separating the regions completely and not letting them interact with each other. So yes, you're right, a lot more modeling would need to be done. This was really me just trying to figure out why the heck is this eastern region so different, and then staring at the white light image and realizing, oh wow, look how the prominences line up. And in fact, you can see with this prominence, there's a significant drop in the cold ion and a spike in the hot ion. You can kind of see that with this too. So there's just this mysterious behavior, and yes, it's not fully explained, that's for sure.
Shania first, and Rolf.
I just wanted to comment for Jeff. Actually, it's not true that the prominences are always associated with active regions. So this is also, there are the polar crown filaments extend all across the solar surface.
Rolf?
So I have a general problem with that. So, the plot as you do there is sort of suggesting the freezing zone is in the plane which I show there, but actually you see an optically thin 3-dimensional image. So you have material in front and you have material behind, which also contributes to the emission. And in principle, you need to disentangle that. And even more, since the full width of half maximum of the filter is 5 angstroms, with an outflow velocity of 800 kilometers per second, you can be shifted out of the filter because of the Doppler effect. Are you capable to correct for these sort of more complicated?
Yeah, that's a good question. I thought about that a bit. I haven't gone into too much detail. The nice thing is, though, if you think about the projection, right? So if you have solar wind coming out, say in this direction, by the time it gets into your projected field of view, the density here is so much lower than it is going this way, that the highest density we're observing, and therefore the most light, is actually in the plane.
That is true, but the path length, on the other hand, is longer.
True.
Where you see.
Yeah.
I think you can model that probably.
Yeah, that would be an interesting way to improve it, certainly. Yeah, that would be interesting.
So you mentioned that the definition of the freezing location
is
based on the point at which the slope becomes sufficiently flat.
Yes.
How are you defining sufficiently?
Okay, 1 second. I thought that I didn't want to show math, but here's math. So basically, yeah, so part of the problem is the lines behave very differently depending on the region, but essentially I just say, okay, take the value of the ratio at a point in a window and look at the absolute change in that window. Is it greater than a threshold I've defined? You know, it has to meet that, and then the gradient, the absolute gradient at the location has to be below a threshold, and it has to be below a minimum freeze-in. So the motivation for the minimum freeze-in is sometimes you get those bumps and wiggles. So what I do is separate the corona into many different quadrants where the lines behave roughly similarly, and I just look at the image and say, okay, well, they're all doing weird bumpy things until at least, 1.5 solar radii, and so I can define this, and then based on how noisy each line is, because again, there's a lot of different things that vary, but I mostly set these by tinkering them, but they're quite small thresholds. Like the maximum thresholds I ever use are roughly 3%. And then I define the window based on the length of the line, and it's a relatively small window. And of course, I am double checking all of the algorithm's outputs by eye to make sure it's not accidentally getting a maximum or something like that. But yeah, so there's math.
Okay, that last question exhausted the available time. So we need to go on.